Hello. Let's continue our discussion of different ways to analyze sequences or time series of data. In this video, I'd like to cover autocorrelation, and that's covered in section 5.5 of Wessel's notes. The lecture also draws heavily from Davis's textbook, chapter 4. Now, the autocorrelation method is a quantitative method to identify patterns or cyclicity in a single time series of data points. And the example that Davis gives is a record of gamma radiation intensity from a well log taken from a oil field in Kansas. Now, the well itself is composed of alternating sequences of limestone and shale, and the gamma radiation comes from the decay of potassium 40. The limestones contain a low concentration of potassium and therefore emit a low gamma radiation intensity, whereas the shales have greater potassium content and therefore emit greater gamma radiation. So again, we have limestones associated with low gamma radiation, and shale associated with high gamma radiation. Now, a visual inspection of the core shows that the limestones appear visually to be separated by shaling units of approximately the same thickness. So we can test, so there appears to be some sort of pattern in the lithologic sequence along the core, and we can test that quantitatively using this gamma radiation record. Again, this is gamma radiation as a function of distance in feet along the core. So the question we pose is there a true typical thickness in the shale or limestone, or are the thicknesses purely random? So let's talk about, and so again, we're going to use autocorrelation to test this quantitatively. So let's recall our linear correlation coefficient. And that we called that R. And again, it was the covariance of two data sequences, X and Y, or two data sets, X and Y. And again, it was normalized by the product of the standard deviation of X and the standard deviation of Y. And let me write that out in slightly different terms. Again, covariance between the two data sets divided by the square root of the variance of X times the variance of Y. And if we look at, for example, if we write out the whole thing, we get the sum over all the measurements in our samples of each value of X minus its mean value times each value of Y minus its mean value across the record, divided by the square root of the sum of each value of X minus its mean value squared times the sum of each value of y minus its mean value squared as well, or the deviation of y from its mean squared. So let's look at the numerator term, or the covariance, and I'd like to draw that out mathematically in a slightly different form, because we're going to see this form at various times when we talk about autocorrelation. So the covariance between x and y, again, is the sum for I equals 1 to n. And from now on, the sums that I write will be along or across each value of our data set. I'm not going to always write this, but that's going to be implied when you see the sum sign. And so we have x, the deviation of each value of x from its mean, times the value of each deviation of each value of y from its mean. And those are squared, and those products are summed, and this is divided by n minus 1. So we can if we carry out that multiplication and do some algebra, we find that that's equal to the sum of the product of each value of x times each value of y minus n times the means of x and y, all over n minus 1. And we can write that in a slightly different form. We can write the second term in a slightly different form, because remember, the means involve sums of x and y, and so this becomes the sum of xi times the sum of all the y's divided by n, and again everything is divided by 1 minus n. And we can also write that, we can also factor out, we'll multiply by 1 or multiply by n over n, and we get this expression for the covariance. So I'd like you to just keep this form in mind, because we're going to see this form used at various points in the following discussion. Now, to see if there's any cyclicity or any patterns of repetition in our data set, let's just consider the covariance of this single data set with itself. So in other words, let's here, let's let x and y be the same data set. And we'll just call that sequence y. And so the numerator of our correlation coefficient simply becomes the covariance of y with itself. And we can write that using the form that I just described as n times the sum of each value of y squared minus the sum of each value of y multiplied by the same sum, all over n times n minus 1. And that's also equal to the variance of y. And so our correlation coefficient is equal to the variance of y divided by the standard deviation of y times itself, and that, of course, is equal to 1. In other words, the sequence is perfectly correlated with itself. So that may not come as very much of a surprise, or at least I'd hope it doesn't come as a surprise to you that the sequence is perfectly correlated with itself. And that in itself doesn't tell us very much about any sort of cyclicity or periodicity in the data. But you can imagine that we could compare the sequence with itself, but a version of itself that's shifted by a lag in distance. And if we vary that lag, we can see how that correlation changes. So that's the main idea of autocorrelation. So if we have a look at the function of R, the correlation coefficient, as a function of lag, we can identify any cyclicity. Now, first, let's look at some results that I produced using that well log, that gamma radiation log that Davis provided. And I've written a MATLAB script that reads in the data and does this autocorrelation analysis. And you can download this MATLAB script from the course website as well as the data. Let me go ahead and clear this. So, okay. So here I'm plotting a section of the gamma radiation log. And I'm plotting it twice. One, the black curve is one is the record of it, and then the red curve is the same curve plotted over overlaying the black curve. And this is the curve that I'm going to shift. So at zero lag, the two uh, replicates of the data overlie each other perfectly, and so the correlation coefficient is identically 1. So, but as we apply a shift of the red curve, a forward lag or so to speak, the correlation starts to drop. The correlation coefficient starts to drop. And it drops to a point now to a negative value. And as I continue to increase the lag, here the lag is 8, the lag of 9, etc. At a lag of say 9 to 11, the autocorrelation coefficient is very low. And then as the lag increases, you'll see that these two peaks start to line again, and you'll see an increase in the correlation coefficient, and that starts to occur right about here. So right about here is where we find another point of high correlation, simply because we've shifted the red curve over um, by an amount that matches up those peaks, and then it goes down again. So let's now look and see how to compute this autocorrelation function. But before we do that, I'd like to point out the first warning that we have to consider. In order for this autocorrelation technique to work, we must have a record in which the measurements are regularly spaced. That is, the interval represented in time or space between each measurements has to be uniform or constant along the whole record. Okay, so once again, let's focus on the numerator of our correlation function. So at zero lag, the correlation of the function with itself at zero lag, I'll write that with a 0 in parentheses, again is simply equal to the variance of the function itself. And this again gave a perfect correlation of R is equal to 1. So now let's look at the function after a lag of 1. And in this case, let's go back and look at the result. So we have 0 lag initially. And what I'd like you to point out is this blue region is the region of overlap between the two curves. So if I shift the red curve by 1, the region of overlap actually decreases a little bit simply because, well, I've shifted one curve over to the right and the record decreases by one measurement or one element. So the length of the new record is n minus 1, and the sum is from I is equal to 1, or I equals 1 plus 1, or 2, to n. And again, we're summing the product of y with itself shifted to the right by one step. And the other term in the numerator is the sum, again, from 2 to n of y times the sum from I equals 2 to n of the shifted version of y. And that's all over n minus 1 times n minus 1 minus 1. So that's true for our lag, or tau, which is our lag step, is equal to 1. So for any value of tau, we can write out the numerator of our correlation coefficient as sigma yy of tau, and that's equal to n minus tau. Our record length has been reduced by tau data points, and the sum is from I equals 1 plus tau to n, again, of the product of y with its shifted version, and that's summed, minus the sum of y and times the sum of the shifted value of y. And again, these sums are for I is equal to 1 plus tau to n. The numerator is n minus tau times n minus tau minus 1. So that gives us the numerator of our correlation coefficient. But let me write out the full correlation coefficient, which is normalized by it turns out to be the square root of two variances, the product of two variances. So the numerator again was sigma yy as a function of tau, and we get the square root of the variance of y, or I guess I should say the sum of square deviations of y from over the interval times the sum of square deviations of the shifted version over the same interval. And this is the y sub I with a bar over it indicates the mean of y over the interval I equals 1 plus tau to n. And the y bar with the subscript I minus tau is the mean of the shifted function. So that's just to define my notation there, and I got to square that one term. And if we write this out, the solution becomes n minus tau times the sum of the product of y with its shifted version minus the sum of y times the sum of its shifted version divided by the square root of n minus tau. We have the sum of y squared minus the square of the sum of y, and then we have that multiplied by n minus tau times the sum of the shifted version squared minus the sum of the shifted version multiplied by itself. So this is what I was plotting in my MATLAB script. And I did want to make a note that for n, a lot bigger than tau, the denominator is about equal to the variance of y itself. So if the shift that you're examining, or the range of shifts that you're looking at, remain small, then you could simply put the variance in the denominator as opposed to this larger expression. But if you keep this expression in your MATLAB code, then it'll be true for all values of n and tau. And I do want to make it clear that the sums here are over the interval of I equals 1 plus tau to n. Now, a plot of r tau versus tau itself will give you how the autocorrelation function varies with the step number, or the number of steps. That's really what our lag parameter is. It's just the number of steps that we're shifting the duplicate curve. But what I showed in my example was the autocorrelation function versus the actual dimensional shift. So that's tau times the interval. So that gives us the function versus the lag in feet of our record. Okay, so let's look at that one more time. So again, here I've shifted the function by a lag of 1, which corresponds to, I believe that's 15 feet. That's the interval in which I've sampled this curve. And as we shift it more and more, you may notice, well, you have to squint a little bit, but the blue area actually shrinks in width. The data record is decreasing, and it's again, the length of the record is n minus tau, and so forth, until we shift it to its maximum value, and I've kept the maximum value to be about 1/4 of the total record length. So the other thing I'd like you to note that because we're shifting one curve with itself, it doesn't matter which way we shift the curve. We could shift it the other way, and the autocorrelation function turns out to be perfectly symmetric, as I've shown here, right? So here I've shifted the right, I've defined a positive shift to be a shift of the red curve to the right, where tau is positive, and a shift to the left is plotted on the left side of the autocorrelation function. But again, it's symmetric. So we've noted, besides the central value, which we always expect to be 1, there are some high values, in particular these two very relatively high values at lags of about 280 or 275 or so feet. And remember, we wanted to answer the question in a quantitative way, is whether there is really a typical thickness of the shale limestone sequences, or are the thicknesses purely random? So we need to determine whether this this secondary peak in the autocorrelation is statistically significant. And of course, we're going to do that with a hypothesis test. And when we do that, we can compare the observed autocorrelation function with an autocorrelation function for a perfectly random data set. So for a perfectly random data set, the autocorrelation, the expected correlation, or the mean autocorrelation, will be 0 for all lags. So the known or the theoretical autocorrelation function, which we'll designate as rho as a function of tau, will be 0. But if we repeatedly sampled from a section with purely white noise, we're not always going to get the mean value of 0. We're actually going to measure non-zero values scattering about this mean, and the scatter will have a variance inversely proportional to the record length. So the variance of our measured values of autocorrelation functions will be equal to 1 over n minus tau plus 3. So therefore we can test whether our record is consistent with a perfectly random record by producing a z statistic, which is our measured autocorrelation minus the expected, which is 0, divided by the standard deviation of expected for a random sampling, which is the square root of 1 over n minus tau plus 3. And simplifying that, we just get r tau times the square root of n minus tau plus 3. So remember, as tau increases, our record length is decreasing, and that will then tend to give rise to a greater variances in the measured values of autocorrelation. But so there'll be an artificial increase in r tau if tau gets appreciably large. So I have to present our second warning. And that is to minimize this artificial or the artifact associated with the shrinking of the record length with increasing tau. A good rule of thumb is to ensure that the total record length is greater than about 50 and that tau remains less than a quarter of that record length. It is no larger than a quarter of that wavelength. So in the example that I've shown, I believe the record length that I have is close to 100 points. So we meet the greater than 50 criteria, and I've specified the maximum lag to be a quarter of n. So I've met both criteria in the analysis so far. Now, to finish our test, of course, we have to set our significance level, and let's say 5%. And so the critical z-value is z of 1 minus alpha over 2 for our two-tailed test, and that's z of 0.975, and that turns out to be about 1.96. So I've converted my R values to Z values, and I show my plot here. So this is, instead of R, this is Z versus lag. And the critical value is about 1.96, and that's the solid bar here. And so besides the central peak at very small lag, the two side peaks, or the side peak at about 275 or so, is seen to be significant. It's highly unlikely that this peak occurs purely by chance of sampling from a random record. So we would reject the null hypothesis that there is no pattern or no characteristic thickness of the lithologic sequences in our record, and accept the alternative hypothesis that there is a tendency for cyclicity with over a characteristic thickness of about 275 or close to 300 feet. So that will conclude my discussion of this example that Davis gives on the gamma radiation log. But let's look at a few other examples of autocorrelation functions. And so here's some example functions. The top one is a sinusoidal curve, and the autocorrelation function here also shows a sinusoidal function with peak high values at about 40, at a lag of 40, which is about the wavelength of the sinusoidal curve here. And you'll notice that there's high positive values, which indicate where the peaks of the sinusoidal curve match up, again, perfectly. Whereas there's also high negative values, and that's where the peaks and troughs line up. So this brings us to another warning, in that significantly negative values of the autocorrelation may not be important. These negative values reflect autocorrelations between peaks and troughs, and they inevitably occur with high positive values, as shown by this example. So the strong negative values may not always provide any new information in your autocorrelation function. So you should keep that in mind when you're doing this sort of analysis. And actually, come to think of it, let me return back to the gamma ray log example. I should have plotted both the positive and negative z-value, critical z-values, because the autocorrelation function as well as the z-values vary between large positive numbers as well as negative numbers. Again, the negative numbers reflecting when these large peaks align with the smaller troughs in this example. So if we plot both the positive and negative z-values, we're able to assess which of those signals are significant on both the positive and negative side. In this case, the negative side doesn't show any significance at our 5% level, so we don't really have to worry about them. If they did show a significantly negative value, we would have to we'd have to think a little bit about whether that adds any information about the characteristic spacing between different units, whether it adds any information to these large positive values. So it's important to know what those negative values mean as well as the positive values. The second example is a sequence of random noise, and this shows the perfect correlation with zero lag is for all functions, but autocorrelations that that scatter about the expected value of 0. And again, the variance of this variation is proportional to the record length minus the lag minus 3, or the square root of n minus tau minus 3. The third example is a perfectly linear increase in some value, a sequence with a perfectly linear increase. And you can see that the autocorrelations are very high and also show a gradual monotonic decrease away from zero lag. The third plot is a sinusoidal function with noise, and you can see that the noise converts this perfect sinusoidal function that rises between -1 and +1 autocorrelation to a sinusoidal-like function with a smaller amplitude. And then superimposed on this, Davis superimposes a line function, and this produces an autocorrelation function that looks like a sine, but also shows a long, almost linear trend of decreasing autocorrelation with lag. So another warning arises with this linear trend. You can see that the linear trend can lead to high autocorrelations that don't necessarily reflect any cyclicity in the data. So the warning is that we should ensure that any linear trends are removed if we are looking for cyclicity. So let's keep that in mind when you're doing this sort of analysis. The last examples, I'd like you to focus on this. So here's a case of perfectly random white noise. White noise meaning there's noise at all wavelengths, including the very highest frequencies. And that shows the autocorrelation function that we looked at just recently. Here's a case in which the noise is smooth. It's smooth noise. So it's a random signal, but it occurs over a finite wavelength band, particularly at larger wavelengths. And the autocorrelation function at large lags scatters about the mean of 0 as expected with the variance, again, that's proportional to the square root of the record length. But at small lags, there's an appreciably large autocorrelation, and that just reflects the smoothness of the data. So the last warning is that significantly high values of autocorrelation at small lags may not reflect cyclicity, but just, again, smoothness in the data. So that's the last warning I'd like you to keep in mind when you're doing this, this sort of analysis. So this concludes this video on autocorrelation analysis of sequence and time series.